Okay, the sound should be okay. And then I try to your gallery. Try to see how far I can. Ah, okay, good morning. So, topic today, two topics. Yeah. So if lectures are recorded and there are lecture notes, usually not so many students, so it's normal. Yeah, two topics today. So, we discussed the online mistake model last time. Now we will present the best algorithm possible for worst case errors in this model. Unfortunately, for learning half spaces in this model, there are infinitely many mistakes. We already know it from learning threshold functions. So I will repeat this. And so we will make margin hypothesis and explain perceptron algorithm. It's like what's considered the first machine learning algorithm from 1950 something. So we will discuss it, but then recently there was a really natural nice improvement in 2008, which is really easy. We will discuss it in this lecture, but nobody noticed this. So it's quite impressive, like for more than 50 years. One of the most important algorithms, people completely missed something important. Okay. So first, let's think again about online mistake model. So there are two players. So there is predictor and challenger, and then there is a supervisor. So in the previous model, I will just say repeat it in words. So previous model, what we have is challenger. So we have a set of classifiers. So let's repeat notation. So we have a set H, a set X, and a set Y. And so whenever you see one of these sets, always assume they're non-empty. I will not repeat it, it's really boring. So for a long time, Y will be a set of two elements. Okay, and H will always be a set of classifiers. So H contains mappings from X to Y. Set of quests. Okay. Okay. And so after we figure this, we can speak about a game played between players, predictor, and challenger. And there was also a neutral supervisor. That's how I defined it previous time. So predictor chooses a classifier from H. A challenger chooses a classifier from H, and then predictor chooses an input. Sorry, what I'm saying. Challenger chooses an input, predictor chooses a label, and then the neutral supervisor tells whether prediction was correct or not. And so this game is repeated finitely or indefinitely, let's say indefinitely, because the same input can be repeated again in case X is finite. Okay, and so the game is defined for H and some number M. And we say that predictor wins if he can make at most M mistakes. And so online, so what is the mistake bound for the class H? So the mistake bound for class H is the minimum M for which predictor has winning strategy. Sorry. It's maximal M for which challenger has strategy. Maximal M for which challenger has strategy. So it is one difference. So let's do a little example. So let us consider X is just some infinite set, say natural numbers, and Y is equal to the set of indicator function on singleton. So so Y is equal to 0 and 1, and H is equal to the set of all functions X maps to X equal to some point X0, and X0 is in or in X, right? So just indicator on singleton function. So this indicator function, it evaluates to 1 if the condition is true, otherwise it evaluates to 0. We've probably seen it already. Okay, and so let's recall our game. What is the maximal M so that challenger can enforce any mistakes? Or what might be a good prediction strategy? What's your intuition? So let's look from the side of predictor. If this question is too hard, so what should so we have the round. Here, predictor, challenger gives X, gives X1, predictor, say Y1, then supervisor says correct or not. And then it's repeated. So in round T, it says X, T, Y, T, and so on. Okay, so it's clear what is this hypothesis class. And so we pick some point, and if if the input equals to this point, we say 1, otherwise we say 0. So what might be a good strategy for predictor?
Just check 1, 2, 3, and so on.
No. So challenger will give you an input. Predictor will say 0 or 1.
And is it X0 fixed, or does it change every time?
Yeah, every round challenger picks a new. So there is a round T. So in round 1, challenger picks just some input, for example, 2. Then predictor says, I think that it will be 1, the answer. So, but predictor, oh, sorry, I forgot to say something important. Before the game starts, challenger picks a true function in H, and he gives it to the supervisor. And then the game starts. Challenger picks some input, then predictor makes a prediction, and then the supervisor checks this prediction against the secret function. So beginning, challenger choose H, supervisor says whether H of X equals Y. So is game clear now? You need to interrupt me because I explained it previous lecture. So I just assumed I just had to make a refresher, and then I explained poorly. Okay, so again, challenger picks a function from H, and then there are infinitely many rounds. Challenger picks an input, predictor makes some prediction for the label, so it tries to guess the value of the secret classifier on the input, and then supervisor gives feedback. Okay, so let's look to our example. Here, the true classifiers are all 0 functions. So from the view of predictor, this first step is secret. He doesn't see which function, otherwise the game is really easy. So So what, so he said, so the smartest move is to always say 0. Right? On unseen inputs, an input he has not seen before, he always says 0 until he is wrong at some moment. But when he makes a mistake, he knows what is a true function. So what is the function chosen by challenger? So I call it the true function. So that might be yes. Okay, let's do another one. Let's look at interval classifiers. So x0, x, and x1. So it's readable. I should write bigger, I guess. Oh, and also not high enough. So yeah, please say something if what I write is not visible. Uh, then x0. Okay, so here are interval classifiers. Okay, so what do you think is a good strategy for challenger here?
For challenger or predictor?
So sorry, for predictor, yeah, a bit sleepy. Okay, so what might be good?
Maybe also say 0.
Yeah, and begin, yeah.
And when he makes a mistake, then start from like bigger numbers. So he knows.
Yeah,
the
okay.
values.
So challenger always says 0. And then let's assume that on some x still the supervisor said that he is wrong. Okay, so what will be second part of strategy? So then I assume there will start the second strategy. So what will it be? So there are two cases, either he gets a new input below x or above x.
Also say 0.
We could start with binary search for x0 and then x1.
Yeah. Well, we cannot, so challenger chooses the input, so we cannot choose the inputs. The opponent chooses the inputs. So,
For example, no. If our interval is x0 and x1, we could take x0 minus million and x1 and assume that this is our true function and say 1 if x is within the interval and 0 if it's not. And if it's within, then we'll decrease the million to like half million and so on by such.
But how do we get to the x minus million if we don't get the inputs?
yeah.
Like, we
So
don't choose.
how do you know that 1 million
We know
is?
one point which must be within the interval. Yes. Then we take the interval to be, for example, this point minus 1 and this point plus 1.
Okay.
And we try to proceed with this.
So if challenger chooses x tilde plus 1, then you say yes, and otherwise you say no.
Yes.
And so you continue doing this until you are wrong again.
Yeah.
And so how many mistakes in the worst case for your algorithm?
Infinite many.
Okay.
There is, I believe there is no good algorithm because the challenger could always say no. Would always be wrong about our interval. And because there are many natural numbers, there is a way challenger to always make us be wrong.
Well, in this version of the game, challenger chooses. Okay, you're basically right. So I didn't think very well for this example. Let us take another example. So you're right. It's always infinitely many mistakes. So let's take another X now. So let's take numbers from 1 to 7. Or let's make it a bit easy, -3 to -2 till 3. So we have 7 numbers going from -3 to +3. And the classifier will be threshold classifier. So we will have, we will check whether X is bigger than X0. Yes.
Then M, or how do you call it?
Yeah,
H comma.
yeah. No, so we have a gain for H and a value of
MH. Okay, then it's binary logarithm of 6 plus minus 1.
Yeah. So the idea is that you have less than binary logarithm mistakes. So in this case, we can make at most 2 mistakes by taking halving algorithm. But here, halving algorithm has a nice structure. So below 0, you predict -1. Above 0, you predict +1. And on 0, it doesn't matter what you choose. For example, +1. So, okay. So, but now let's change the game a little bit. So there is an equivalent game. So where we don't need a supervisor. So how can we choose, get rid of supervisor? So we get rid of the first move here. And here challenger can choose the label, but he must choose a label such that at least one function of H is consistent with previous input-output pairs. So challenger. So remember that the set of all classifiers consistent with previous input-output pairs, it's called version space. And it was denoted by VT. So the set of all H and H for which H x1 equals y1 and H x t minus 1 equals yt minus. I forgot whether I skipped 1t or I decreased the index by 1 or not. So version space at around t, yeah. So you look until the previous one.
So you know the answers for this? Like
Well, the version space is defined at around t, and it's equal to all the good classifiers at the beginning of this round. So, for example, V1 is equal to H because we haven't seen any input-output pairs. Okay, and so here challenger chooses so here we have a prediction, and then we have a label chooses YT, such that the version space on T plus 1 is not empty. Okay, I changed the notation. So for prediction, I use Y hat, and I use YT for the correct label. Okay. So when we have finite M, these games are equivalent. Okay. And now I will define little stone dimension, and I will prove that the mistake bound M of H is equal to this little stone dimension. So the maximal M for which challenger has winning strategy is equal to this little stone dimension. Okay, so before I define this, let us define what is the game tree for this game. So the game tree corresponds to the moves of the players. So we have a root, and I will label the nodes. The nodes I will identify with the version space of the game. And so I will label this node by the first move of challenger. So I will label here x1. And then we can define for the two answers. So let us say h is equal to -1 plus 1. So then there are two possible version spaces of our h. And then again, I can label this node by a value of x2. But the label here and the label here does not need to be the same. Okay, so let's say x2 prime. And then we can continue. And in this way, we get the game tree. So we can continue and so on. So let us do an example with threshold functions here. For example, I can choose here x1 equal to 1, for example. And then when the label is equal to +1, then here we have functions f1, f2, and f3. And here we have f-3, f-2, f-1, and f0. Then, for example, here one may choose the value x2 equal to -1. And then we have the label +1 and -1. And so in -1, for the answer -1, we will have the version space f1, f2, and f3. All these functions will say -1 if the input x2 is equal to -1. And for the answer +1, we have empty set. So this is kind of stupid move in the game because it doesn't reveal any information. So let's on the other side, let's make him a more clever move. Here, for example, x2 equals -2, and then we will have f-3 here, f-2, and f-1 here. So this is more clever move. It at least this game reveals information about the true classifier. So this is an example of a mistake tree. It's just a part of a game tree.
And where do we get those f1?
So that's the version space. Here I write the set of classifiers that are consistent with the moves. So here move of challenger. On the edges, the moves of the predictor. So we get a binary tree. Each node has either 0 or 2 children corresponding to a game and the move. So mistake tree, yeah, just part of game tree, and the nodes. In the nodes, I write the version space. Okay. So we say that mistake tree is shattered if every leaf is non-empty. So it's annoying to write the definition of mistake tree, but we say that mistake tree. That's right. These are non-empty. Okay. Then a perfect binary tree. This you know, right? It's a tree of depth D. All the leaves are at depth D, and all other nodes have degree exactly 2. So number of nodes in binary tree of depth D is 2 to the power D plus 1 minus 1. Okay. And so now we can say what is little stone dimension. So the L dimension H is equal to max size of mistake tree that's a perfect binary tree, or let's say max depth of perfect of a mistake tree of a shattered mistake tree that is perfect binary. So this is the definition, but let us think a bit more why this definition is so interesting. So if we have a mistake tree, a mistake tree defines a strategy for challenger. But for example, whenever a node has two children that are non-empty, challenger can enforce a mistake by making the corresponding move, right? So if all the leaves are non-empty, it means that so here we have a tree, a perfect. So here we have a perfect tree. That means it gives us two moves for challenger, a move of depth 2. If the tree is shattered, then all the leaves correspond to valid sequences of moves. Here it's not the case, so let us choose +2 x equal to 2. Then here we have f1, and here we have f2 and f3. F0 disappeared, -1. But I am writing nonsense here, so +1, and no, it's correct, yeah. I've got a bit more. If we choose -2, then the label is only f-3. Here we have f2. Okay. So here we the mistake tree gives us a strategy for challenger, and this strategy can enforce the number of mistakes that it can enforce is minimal depth of a leaf. And so if we have a perfect binary tree of depth d, it means that challenger can enforce d mistakes. And so from definition, we directly see that maximal number of mistakes challenger can enforce is at least the little stone dimension of each. So now we want to, so there is a theorem, and it says that it's actually equality. So the theorem says that little stone dimension of H is equal to M of H. So this provides us with an optimal prediction strategy. So to prove this, I will present a prediction strategy whose worst case number of mistakes is exactly the little stone dimension. So we have finite game with perfect information, and then there is general theory that precisely one player has winning strategy. So just by presenting a strategy that makes this many mistakes, we are finished to prove the theorem for predicting. So what is the strategy? So strategy is so we receive xt, then we predict a label that transforms the version space, if it's true, transform version space to the one with largest little stone dimension. So that's our strategy. So we predict YT hat equal to argmax of the little stone dimension of our version space in the current round. So argmax over Y tilde. And here, I mean the version space after adding the label Y tilde for the input X T. And then we receive correct label. So this is our strategy, repeated infinitely often for challenger.
So we choose like the last correct function.
Okay, so let me clarify. So the question is, so we receive xt, we need to make a prediction y hat t, and we will look at both possible values or at both possible answers and think that it's true. And we will look to the version space assuming y tilde is true.
Why not argmax?
Argmax we will take. It will be clear in a second why we take argmax. Okay, I will write explicitly what is y tilde is just equal to all h in the version space at time t for which h xt equals y tilde. And before I explain, so now there is a claim that this algorithm, maximum number of mistakes it makes, is little stone dimension. And before I prove this, let us look to the input that we receive from challenger. So we at a given moment, we have the version space t, and we look to input xt. And I claim, so let us say that little stone dimension of this version space is some value m. Let's say m tilde, no, m is not in use, so we can, so then I claim that these two possible version spaces, they cannot have little stone dimension m as well. And so as the game prolongs, little stone dimension of version space decreases. And I claim that it cannot happen that both these version spaces have dimension m, little stone dimension m. Why is it?
So then L dim of this T must be at least m plus 1.
Yeah, exactly. Okay. So, and what is the mistake tree, perfect binary mistake tree? How do you construct it?
So we pick the depth, for example, the depth m from the left side and from the right side.
Yeah. So what we have here, so here we have this version space fp, let's say -1. And here we have the version space vt plus 1. Between, if we assume that both these spaces have dimension m, then there exists a perfect binary shatter tree of this version space. This is a tree of depth, perfect binary tree of depth m. And here we also have a perfect binary mistake tree of depth m. So when we combine them using our label from challenger, we get a mistake tree of depth m plus 1. But this contradicts our assumption. We started with depth m. So we know that one of these two version spaces must, at least one must have dimension less than m. And so now can you finish the proof?
Yeah, so if we make a mistake, then the L dimension decreases by at least one, so we cannot make more than L dim of V sub 0, so of L dim of H states.
Yeah, exactly. So should I repeat this?
Yes, please.
Okay, yeah. And people from home, maybe my sound was off, but you should also speak, because in the beginning of the lecture I was saying nonsense and forgetting all the half of the relevant things, and you were just sitting. That means that everyone is wasting the time, and the YouTube movie will be very bad. Okay, so let me repeat this. So we understand that one of these version spaces, it has dimensions strictly less than the dimension space of VT. A little stone dimension of version space in the beginning of the round. And so we, when we are wrong, we will end up in a version space with the little stone dimensions strictly smaller. So whenever we make a mistake, so we choose the little stone dimension that's maximal. And we know that at least one of the version spaces must have smaller dimension. So when we are wrong, it means that we arrive in a version space that's strictly smaller. And so the only way that the version space does not decrease is if the label belongs to a version space that does not decrease the little stone dimension. So whenever we make a mistake, little stone dimension of version space decreases by 1. And so after m mistakes, we will end up in a version space with little stone dimension 0. And now there is an interesting question. What happens? What is maximal number of classifiers? So I claim that if little stone dimension of H is equal to 0, then size of H is equal to 1. Equal to 1, yes. So then we know that we can predict all inputs. But why is it true? So say that what is definition of little stone dimension?
If it's bigger than 1, then we can build at least the tree of 3 nodes. So
yeah,
so
the
just
root and 2
divide
children.
them.
Yeah, but we cannot even build this perfect binary tree. So that means biggest shattered binary tree is the one that only contains the root. So the tree of depth 0. And so we cannot find a value for which 2 different labels, we cannot find a classifier for, we cannot find 2 classifiers that disagree on a single input. So it says that on every input, the set of classifiers in H agrees on the label. So, okay, then it's clear what function is in this version space. Okay, so let us show that. So this is the borderline case. So at any moment, yeah, so. So formally, you need to make inductive argument and say by induction on M, we prove that the little stone dimension is at most number of mistakes made by the strategy and so on, and then talk about the base case. So I've done this in the lecture notes. Okay, and this finishes first part of the lecture. About so now you know when we are interested in this model, In the online mistake model, there is just a single perfect algorithm. That is a best possible strategy. And so this will be the last place where we know what is the perfect strategy, how we optimize our a mistake bound or risk bound. So all other models we will see, it's ongoing research. So for machine learning, we want to have risk bounds, but upper and lower bounds, they differ by a linear constant. So to know from this theory what is best possible machine learning algorithm using expected error on test set, it's not yet possible. And unfortunately, the linear constant between upper and lower bound is more than 10,000. So that should be a critique, like people say, the risk bound status machine learning algorithm should be of this and this form. In order for this argument to be convincing, you want risk bound with like 1 plus epsilon error, optimal to, or even much better, like perfect. But so this is a serious weakness. But okay, there is no other theory. So hopefully, when you are old, there will be nice theories, or maybe in 10 years if things go well. Okay, but that's enough blah blah. Let's now go to prediction of half spaces in online mistake model. Okay. And so we already said before that there is an obstacle when we are learning threshold, and we've seen the same obstacle just in the beginning of this lecture. When we are learning thresholds, we can be always wrong. And so our plan is to limit the interval on, so we will learn threshold on real numbers. And the plan is to limit the interval on the outside. So we will say the norm of the inputs have to be at most a certain value, but also the inputs should stay away from the true threshold by at most certain margin. And then we will have a mistake bound given by the ratio of these two numbers. So what I'm saying is, so that is just right without any gain. What is the, yeah,
Like about the previous theorem about the.
yeah.
We say that y can only be equal to -1 or +1, right?
Yeah, I just choose these labels for everything in the lecture, but it doesn't matter how you name the two elements.
Okay.
Yeah.
Just like binary classification.
Yeah. But now for hyperplane, so in 10 minutes, it will be important for notation. Yeah, that's why I fixed it. Okay, but let's do the easy example. And so I say that there exists prediction algorithm that on and so now I write the infinite list y1 x2 y2 and so on, and we bound the norm of the inputs, so you require them to be at most r such that there exists a threshold. So note that here I'm using x. So I will use x equal to -r. Sorry, I will use one dimension. So that's right. R, so that there exists key with I minus D yi bigger than rho. Let me write a bit better. So I assume that for all I. Okay, what is this complicated formula here? So we want to learn a threshold function, and we will think of t as a true threshold. And xi minus t is equal to +1 if you're above the threshold, -1 below it. And here we use the labels yi. So we will use y equal to -1 + 1. So already now it's important for these labels so that we can use convenient notation here. And so it means that we get the correct answers are indeed correct, and we have a margin here of absolute value, at least some rho. So there exists a true threshold, and then our prediction makes at most, and here we have a logarithmic number of mistakes, so binary logarithm. So I will use log will always use binary logarithm, and sometimes I use ln, and it's natural. So this is ln is natural logarithm, and it's like common in computer science, but for some time we don't need it. And so maximal number of mistakes is equal like that. So we have logarithmic number of mistakes. And so this is basically, again, the halving algorithm. But here, the hypothesis classes all threshold functions for real numbers. So here I'm using real interval here. Sorry, I didn't tell. So now we cannot count cardinality of version space. But so when we're making predictions, let's make a small picture. We have -r0 and +r. So we know at any moment the true threshold is, so at any moment we can define the versions, an interval of thresholds that are in the version space. Initially, if we haven't seen any data, the threshold can be on any place between -r and +r. But when we receive labels, the possible true threshold labeled input-output pairs, the true threshold interval decrease, the version space decreases. Corresponding intervals become smaller. And so our plan is so at any moment there will be an interval through thresholds corresponding to the version space, and we will predict minus at the left half and plus at the right half. So we split it in the middle. And so now we can understand why this result is true, okay? And because each time we make a mistake, it means we predicted the wrong label at half. And so that's, so here we have an interval. We will divide it in two, predict minus here and +1 here. If we receive a point here and its true label is plus, then the version space, so when we receive a point here and it turns out to be plus, then our version space interval decreases by more than half. So when we make a wrong prediction, we lose at least half of the version space. And so that's how we prove this result. Okay. Now, this is for one dimension. It's easy. What happens in more dimensions? So this is explained by perceptron algorithm. So what will I change here? So now we have x. X will be all inputs. So x will belong to RD. So I use the letter D for input space, and the norm of x is at most D. So I use the same labels. And now result changes here. Okay, I also need to say what, how to replace this quantity. What does it mean to stay at least a row away from the margin? Okay, then
And is the D, so the normal X is not bigger than D, yeah?
yeah. Sorry, of R. Yeah, this is a mistake. D is the dimension. Yeah. So the first thing, to simply express this problem, we will focus on homogeneous half spaces. So the half space, the border goes through the origin. So we will be interested in X classifiers of the form X times W, so indicator. Or let's write it differently. We have the sign function X times W. So sign function in machine learning, it's the same as the normal sign function, except in the value 0 where it's mapped to +1. So sign is element of -1 +1. Okay.
And what is W?
So for each so the set H that we consider here, W and RT. So X is also in RT, the same like W. Okay, so they're not half, so they're in general, you might have half spaces whose border is not through the origin, but this is kind of connected. And so if you're interested in half spaces of this form, sign of this form, you can make a transformation. So W goes to the vector WD, X goes to X met with 1 at the bottom. And so then here we have a similar thing as sign X prime times W prime. So where X prime is defined like this and W prime. So this is very similar, but it's kind of a bit tricky because we will look to the norm of W. It will play an important role here. And when we append this constant, sorry, I write D, I mean, of course, B. So when we append B here, it goes inside the norm. So it's kind of like when you want to implement something, you need to think about this, that when you switch this, you change something in the theory. Okay. Yes. So we will speak about homogeneous half spaces. And now we know how we can compute the distance between the border. And so we have some hyperplane. And then we can look to the normal vector W. And then is the question how we compute the distance from point X. So here we have a point X and we want to know the distance to the hyperplane. So for this, we just project X to the normal value. So distance of vector X and the hyperplane. Okay, I will just write hyperplane of W. It's equal to X times W divided by norm of W. Right, but this is a sign distance. So it can be negative or positive. So the sign distance, but the sign is actually useful because we want to know whether or we are interested in the sign of this thing. So what I'm saying is that here we replace the condition by the following. We require that so W divided by O. I will use W in the algorithm, so let's change the letter here. Okay, so you want that there exists a hyperplane V, a normal vector V, for which position xi is at least, so the distance of xi from hyperplane is at least rho. And we also want that xi is on the right side of the hyperplane. That's why we multiply with the label, which is -1 or +1. So here we consider a set of inputs that are classified correctly by at least one hyperplane, and moreover, the inputs stay away from the border. Oh, and we use this picture. So here we have x1. So the positive labels are here, the negative labels are here, and we should stay away by a distance rho on both sides.
Now, may I ask?
Yes, yes.
So we not only want to predict the correct label, but we also want to like x multiplied by w to stay to be like some.
Yeah, not too close to the hyperplane.
Okay.
And under these conditions, we can get away from this problem that we make infinitely many mistakes. And the bound now is, unfortunately, it is not so good. So it is makes at most it is now not logarithmic plus, but r over rho squared. But at least there is a finite bound now. So this is perhaps oldest machine learning theorem, 1954 or something by I forgot now, but it's in the, it should be in the course, in the lecture, in the, well. I hope I wrote it in the lecture note. So the guy in the 50s, this very young guy, he was less than 30 years, and he was specialist in electronics. So he built huge machine, probably bigger than this thing, to classify pictures. So he had also to build a first camera so that people could put pictures there, and he could digitally scan it. And then he ran this algorithm to classify pictures. And then there was a news, like in the most important American journal, it's from the US. So here in Russia also there were such things, but I don't have any information about it. But in the US, they put it on the most important journal on the front page that they discovered, they built a machine and they discovered a concept that will be the beginning of artificial intelligence and the beginning of something that will start to think like humans and will become more clever than humans. So that was for general audience. So there was some hype in artificial intelligence and AI. So I don't know, probably at that time for normal people, it was unimaginable that there is something that's clever that's not human. Like I remember that my grandmother said when she was little, so her grandfather said that, look, soon people will be walking on the moon. And everyone said, no, impossible. It will never happen. So it's on. So I don't know, but now it's like a bit on the other direction. Like many people, like stock market is going down now, and the central banks are pumping money in the world for because people realize they overestimated ChatGPT a little bit. So okay, but should not be speaking now. I mean, this is very interesting, but I should prove theorem. Let's prove this theorem. Okay. So all these definitions we don't need, it's just introduction. And so, so there is a question, if you have a data set, let's even think about offline, fitting a hyperplane to binary label. So how could you do it? So maybe you learned about linear programming. So you have a bunch of inequalities, so that would work. But that's a real advanced algorithm that doesn't work in practice. Like a linear program, it's in the class B and the algorithms exist. But as soon as you have a few hundred inequalities, you might be unlucky and it's not so reliable. Okay, so let's think about 2 dimensions. So we have stars, and then we have some bullets. So how can we compute a separating hyperplane? I need, so here in this case, just a line if there is a, how can we find the computer line directly? So one naive idea is just like, okay, let's take the center of gravity of all the stars and of all the bullets, and then look what's happening in the middle. And so you might be lucky that this separates, but you can invent counterexamples. And so if there are like many stars here and just one star here, and then there are many balls here, and just one ball here, it's not gonna work, right? Okay, and so the solution of our hero from 1954 is just iterate over all data points. And so, okay, so let me write the solution. So we could say that is just equal to yi(xi). Center of let's say the data set is balanced. Then we would set w equal to I equal 1 to, okay, there are t points, right? So that would, but his idea is just a little bit more clever. So he says, let's iterate over all data points. And so let's maintain some normal vector w, that's initially the 0 vector. And then iterate over all data points. Whenever the prediction is wrong, I will add yi(xi) to w. So that is his prediction strategy. And that's the strategy that works for this bound. So let me write it in full detail. And so we receive xt and around t. We predict the sign. Oh, yeah, sorry. W1 is equal to the 0 vector. Then we predict yt hat is equal to sine of wt times xt. Okay. Then receive the true label, and then if yt not equal to the predicted label, then we set wt plus 1 equal to wt plus yt xt, and else wt plus 1 equal to wt. So this algorithm. So intuition is very clear. So imagine that this is our wt, and we receive xi. Let's say, sorry, we receive xt, and yt is equal to plus 1. then we have a problem. So corner more than 90 degrees, that means we predict -1. And then what will happen is we will add here there is also xt, and this will be wt plus 1. So slowly wt will rotate through the correct direction. And so what he was doing is just iterating through all the data several times until 0 mistakes were made. And this theorem promised him that if there exists a good separating hyperplane, after a certain number of iterations, he must find the hyperplane. Okay. Yeah, so now let us prove that this algorithm indeed makes at most this many mistakes. So here V is special vector, which is like the true solution. It can play the role as a true solution. There can be many true solutions, but okay, let's refer to V as true solution. And so idea of algorithm is that so we will prove that Wt is rotating towards V. So we will look to the projection of Wt on V. So note that V, we can rescale V like we want. So let's use for V a unit vector. I remember this. And so that now let us have V equal to 1. And the first step, let us see what happens with the projection of W on V at a mistake. So at round with mistake. At round with mistake. Then let's look to Wv plus 1. And so let us expand the definition of Wt plus 1. It is equal to Wt plus V times xt yt. Okay, what do we know about this dot product? Yeah, so at least rho. And because here we assume V as unit vector. So this dot product at least rho. So the sign is correct, but even more, it's at least rho. So we understand that this is V times Wt plus rho. So this is our first observation. So to prove that it's rotating, we see that projection increases linearly in the number of mistakes. Now we will prove that the norm of W increases by the square root of the number of mistakes. And so that means that the norm increases of W increases much slower than the projection. So we conclude it is rotating towards V, but also projection cannot be larger than the norm of Wt. So after a bounded number of mistakes, the process, there will be no more mistakes. So let us inspect the norm of Wt. Wt plus 1, the squared norm. So now our advanced algebra. So we expand the definition of Wt plus 1, we have two terms. So again, the same thing, Wt plus xt yt. And now we use, we expand the product. So we use this dot product, Wt times xt yt plus norm of, so I can drop yt, right? Okay, so that's right, doesn't matter. Okay, this equality clear? Now, what do we know about this thing? Remember, we are at round with mistake. So what do we know about this?
Double,
It's
at least double row.
no, it's W, not V.
Yeah, sorry.
Yeah, but
Uh,
yeah. So what do we know about the sign of this thing?
hmm,
minus.
Yeah, it's negative indeed. So we know that this is bounded by, so we just drop this WT squared, and we know that this is at most R squared. Because we assume input solve of xi not equal at most R squared. So this is at each round with mistake. So we see the normal W increases by R squared. Okay. And now we can combine this thing. So now we will say that projectional unit vector is smaller than norm. So this is Cauchy-Schwarz, yeah. I'm going. So we have. Yes, I'm 42, but apparently I'm already close to C now or something. Okay, so Cauchy-Schwarz times G. So we know that this is bounded by 1, so we can drop it. So this is exactly equal to 1, the V. So we have this thing. And now we insert our inequalities. So we know that so we have that this number of mistakes times rho. And so let's take the square of both of them. So we see that m squared, rho squared is smaller than m times r squared. And so now we are done because we can cancel m and we have the bound for the remaining m, which is this thing.
And how do we know that V multiplied by WC is greater than?
Then r squared. Well, initially W1 has norm 0. And at each mistake, we prove that at most increases by r. So after m mistakes, norm of W is at most m r squared. Oh, and 7 minutes left, but also the recent improvement I need to tell, but it's not so much work. But to tell the recent improvement, I will change the formulation of the theorem. So I will fix a scale and I will set, before in the proof, I set norm of W equal to 1. Now I will set this dot product to be at least rho. So I take a bigger normal V. So I will just delete, simplify this theorem here. And so I will rescale rho by, so I replace rho by the norm of V. And so what we have here, so I will have R squared norm of V squared mistake. Sorry, I will replace rho by 1. So then the rho in the previous version needs to be divided by norm of V. So here in this result, okay. And so then the proof actually simplifies a little bit. So now I don't have this anymore, but so here we don't have, so I replace rho by 1. So in the proof here, there will be a 1. And here I will keep norm of V here. And so what's changing here is that this rho becomes 1, but here we have V squared. And so you can see the proof now becomes easier with this scale. But interpretation of the theorem is a bit stranger now. So it's normal that for the first time I show it to you, I use a natural interpretation. But this technique keeping the margin bigger than 1 is the most common scaling. In SVM, you will also use this scaling. Okay, and it's important for formulation of the new theorem. I need to delete something, but I really need this thing. So I will delete the algorithm. Okay. Now we will look to the agnostic setting. We will no longer assume that V satisfies this condition. And then we get a little bit more, we get more mistakes. So let us delete this assumption. But now the number of mistakes is a bit more. We will need to add plus sum over all I to plus infinity max of 0, 1 minus. Okay, I need more space. Right, small, and then R squared normal V squared plus sum 2 times max of 0, 1 minus yi xi. Missed. So here is the theorem. So it's theorem by Morty, the same guy who wrote the book that we will be using. So this is true for every V, every normal vector V. But of course, you want to choose, so sorry, I'm wrong. Here I forgot to multiply by V. So what we have here is the scaled version of the margin here from V. So the theorem says, so there is a special case. In the previous version of the theorem, we had that this was always negative. Margin was always at least 1 in formulation of previous version. So this maximum was always 0. That's how we get the previous version. But now it says that if we manage to have a V for which this margin error is reasonably small, then we make few mistakes. So it may happen that there are a few points, that there are finitely many points that are on the wrong side of the hyperplane. But then when we go through the infinite sequence, still the number of mistakes will be bounded. And so we need to prove this theorem, and then the lecture is finished. So there are 2 minutes left. And maybe we can even do it, if I remember it. Okay, so the first, so B doesn't change. Nothing changes here. Because we didn't use any assumption about V for B. But for A, we need to change something. And here we will say that this is bigger than 1 minus the maximum of 0 and xi, sorry, xt, wt, and y. So instead of adding 1, I add 1 minus margin error. So that should be trivially true. So here I'm using, okay, but sorry, here should be a V. Okay. And so this inequality, something is wrong here. sorry, I didn't copy the max correctly. So 1 minus YT xt times. Okay, and now it's right. So now we have that this is trivially smaller than this thing here. 1 minus maximum of this thing. So if the maximum was not here, then we could cancel the ones and we have the same thing. But now we subtract something that's larger. So this inequality is still true. And now we just need to fix the end. So here on the left side, we have m times rho. Now we need to subtract something. So before we had just m, I forgot to drop the rho. Now we will have m minus all these terms. So let us say that L is equal to the sum of 1 minus maximum. Sorry, L is equal to maximum 0, 1 minus YT xt times m over all. So now I have that m minus L. So m minus all these error terms, all this correction on the equation. And now we follow this thing here. So now we have to compute the square here. So now it's not m squared, but m minus L squared. L squared is smaller than this thing. Now let us expand. This is m squared minus 2ml squared. This is smaller because I dropped the L squared term. Okay, and here, now let us look to the final inequality. Everything has an m, so we can drop the m. We can divide by m. And then we have an upper bound for the remaining m. So let me drop all the m's. So the square drops, this m drops, and this m drops. And what we have is m minus L is smaller than r squared v squared. In other words, number of mistakes is smaller than r squared v squared plus L. 2L, sorry, 2L, but there is a 2 here. So this finishes the proof. Okay, so now you're specialist in perceptron algorithm. So there is kernel technique, and it's written in the notes, but I will postpone teaching it till later. But you can read it because it's very interesting. Yeah, and then we will have homework. So so ideas that let me. Okay, I'm already over time, but just 30 seconds. So idea is that this is to fit linear spaces, but sometimes, like even if just one dimension, data might not be separable. So if you have blocks and circles, this is not linearly separable. However, if you remap the data to quadratic, so if you put if you here you replace the input x by x squared, so you use a polynomial remapping, data becomes separable. Right, so you can linearly separate. So the idea is to remap the data. And the thing is with perceptron algorithm, you can change the algorithm to only use dot products. So you can make a remapping of the data, but you don't need to compute this remapping. for polynomial remapping, you can compute these dot products in a very easy way. It's called kernel technique, and it was discovered more than 100 years ago when there were no computers and people had to be clever with manual calculations. So computer means a person that for his profession just make computations by hand. And so they were very clever in saving computation time, but now it's again very important because it's more data. And so this kernel technique is just used like so many places, and it can be applied to a perceptron now. This is a small advertiser. So you won't need it for the next month and a half, this kernel technique, but we will use it again later. And then we will go back to the perceptron algorithm. So there is in the homework, there is an exercise from the previous seminar that says that there is a problem where a perceptron algorithm makes exponentially many mistakes in the dimension, around 2 to the power d mistakes. But then we will apply the kernel technique and it will decrease to polynomial and d many mistakes. But the second part of homework is later. Okay, so let's finish the lecture. See you next week. So sorry for a sloppy start of the lecture. I will be more careful next week.